is total rainfall. And this intensity, which is lasting for TC hours duration, that rainfall intensity which lasted for TC hours duration, or during TC hours duration, whatever was the maximum rainfall. TC is time of concentration. We'll see all these terms one by one. A is catchment area. So A we are aware, Q50 we are aware. Now let us say these three, C, I50 and TC, what they are and how do we determine. C is runoff coefficient. This basically tells you how faster your runoff, once any water falls and which converts into surface runoff. Whenever there is any water falling on any surface, a part of it becomes runoff. It goes into runoff and balance part where it goes? इसको क्या कहते हैं? Any idea?
Infiltrate कर जाता है सर कुछ depressions में.
Infiltration, exactly. Runoff and infiltration, and this infiltrated part is what later on converts or gets converted into base flow. Okay, so how fast is the runoff? That is what your runoff coefficient shows. If it is concrete, it will be very higher value, water will come immediately. If it is grass or different type of soil, it may come slowly, runoff coefficient will be less. So it depends on nature of soil. Like clay soil will be faster, sandy soil will be slower. Soil cover also, barren land travel faster, green vegetated land will travel slow, and location of catchment also. Location means basically slope. So depending on this RBF 16 gives a table. Depending on description of catchment, this is formula for C, sandy soil, sandy loam. Here, this part is common, R into F to the power 0.2. What is R and F now we'll see. And this coefficient only is different and it keeps on increasing as we go down. Then from sandy you come to alluvium or silty loam or coastal areas, red soil, clay loam, grey or brown alluvium, cultivated plain, tail crops, wooded area, black cotton, clay soil, lightly wooded, like that description, hilly soils, plateau and barren land. That is description of catchment. Depending on description of catchment, value of C is given. Now issue is R and F. So we'll see what is R and F. R is 50 years, 24 hours point rainfall. In that catchment, there are at that point where your bridge is located, what is 50 years, 24, basically R 50, 24 in centimeters. That is R, where R is written in previous equation. And from where do we get? We get it, there is a figure 1 in this RBF 16 report. In this is the map of the India. Then there are, these are rainfall contours like this, 200, 300 like this. So you will try to find out where your bridge is there. Let us say your bridge is here. Then you will take this contour and interpolate and find out for this. So this is figure 1 of your RBF 16. From there, you can get R50, 24. Here you can see there are longitudes 60, 70, 80 like that. And this side is latitudes. So for your bridge, you draw the lines and wherever your bridge is there, for that location, you calculate your R50, 24. And what is F? F is aerial reduction factor. Now, this is my catchment area. My rainfall is somewhere here or maybe at 2 rain gauging point. And its effect I am taking over whole of the catchment. That is what averaging I am doing. So for converting this point rainfall into aerial rainfall distributed over an area, I apply a aerial reduction factor. Its effect over complete area will be less. So this factor will be always less than 1. So this is called aerial reduction factor. It again depends on catchment area and duration of rainfall. For that, this RBF 16 has given a table. In this table, this side is catchment area less than 2.5, 2.5 to 5, 5 to 13 and 13 to 25. Because your small catchment area is only up to 25 square kilometer. This side it has taken duration of rainfall, which it takes equal to TC. TC what is there we'll see. So if this duration is less than 30 minutes, this value, 30 to 60 minutes, this value, and 60 to 100 minutes, this value. It does not give more than 100 because most of these small catchment area, the TC normally comes less than 100. But in some case, by chance, it will happen very rarely. If it goes more than 100 also, you have to pick up this column only. So this is about, and you, as I told you, all these values will be less than 1 because you are distributing point rainfall into area. Effect will be less. So now we have taken R also, we have taken F also. Knowing R and F, you can calculate C depending on your nature of catchment area. Now let us say you cannot, yes.
सर जो हमने कैलकुलेट 50 years 24 hour point rainfall कैलकुलेट किया था सर, उसमें 24 hour कोई भी सक्सेसिव 24 hours है या सर एक पर्टिकुलर डे का ही होगा सर वो?
नहीं, इन लास्ट 50 years 24 hours में जो मैक्सिमम रेनफॉल हुआ पिछले 50 साल में, दैट विल बी R50.
नहीं सर, वो 24 hours हम जैसे अभी आज सुबह 10 बजे से कल सुबह 10 बजे तक देख सकते हैं या फिर आज का मतलब एक डे का पर्टिकुलर लेना पड़ेगा?
Normally see what happens is, I will tell you this when we go further. जो whichever rain gauging or catchment area instrumentation is very old, there what they are able to do is they are able to capture hourly rainfall data also. So wherever hourly rainfall data is there, then they will say any 24 hours whatever is maximum. But this is for whole of the India. If you see the figure 1, and for whole of the India, hourly rainfall data is not available. What they have taken is once in 24 hours. So they are having sometimes a morning 7 o'clock and next day morning 7 o'clock. So 7 to 7 or 8 to 8, that interval is fixed. But there are some of the catchment area where hourly rainfall data is available, which is most accurate. We'll see when we go further. There we use that data. Okay.
Okay, sir. Thank you, sir.
In case your description of catchment is not very clear or it is not available, because this value of your C is based on description of catchment. Let us say your catchment is very widely varying from one point to other, or you are not able to describe in those terms, then you can also calculate approximate value of R by using a regression equation, which is given in RBF 16 itself. There C is given 0.537 R50 TC to the power 0.179 into TC to the power minus 0.1. So now you can calculate by this also, but for that you will need R50 TC value. From where to get R50 24 तो हम figure 1 से ले लेते हैं. R50 TC कैसे निकालेंगे, and TC, how we will get TC and what is TC. So this will be required. R50 TC is again 50 years TC over rainfall value, and T is time of concentration. So first come to time of concentration. First of all, I think you must all be knowing what is time of concentration in a catchment.
Yes, sir.
ये तो आप सबने पढ़ा होगा. What is time of concentration for a catchment?
So farthest point से outlet तक आने में जो time लगता है.
Very good. हमारा ये जो catchment है, जैसे ये catchment था, इसमें हमारा ये farthest point था, वहां से यहाँ तक आने में जो time लगता है. So its physical significance is at the end of TC hours, if my rainfall continues, all my streams will be contributing to the flow here. It means from TC hour onward, TC hours maximum flow will be built. From there only build up will start. So that's the concept of TC. So TC कैसे निकालेंगे time of concentration? Normally we use a formula which is known as Bhatnagar formula. This RBF 16. There are many formula, but RBF 16 recommends using this formula. And what is Bhatnagar formula? This is derived for Indian catchment areas, except few catchments, which you will see. It says TC equal to L cube divided by H to the power 0.345. L is length of longest stream course from source to bridge side. Catchment area property से मिल जाएगा. H is height of farthest point above the point of interest along the river in meter. Length elevation profile से मिल जाएगा. तो L और H मिल जाएगा, हम TC calculate कर लेंगे. But RBF 16 says, number one, in west coast and other similar region. What will be called similar? where the slopes are very steep. See, if you see all our hydrometeorological zone of India, west coast is one such where slopes are very steep as compared to your other areas. So there Bhatnagar formula does not apply, and their length is relatively small. The length of stream L काफी small होता है and S ज़्यादा होता है. That is the characteristics of west coast and other similar areas. So it says for those, either you obtain TC from hydrographic analysis. आप hydrograph से TC निकाल लीजिए. You will see hydrograph आप सब जानते हैं, and we will just quickly rephrase it or summarize it after this. और यदि वो नहीं करना चाहते हैं, it says still if you don't have hydrograph, because getting hydrograph is not an easy thing, then it says you use, there is another formula, what is known as Brensby-Williams formula. So for most of the catchments, use Bhatnagar formulas. For catchments having steep slope and less length of stream, especially like west coast, we may use Brensby-Williams formula. And what is that formula? This is the formula. TC equal to 0.605 multiplied by L divided by A to the power 0.1, S to the power 0.2. All these parameters we know. TC is of course time of concentration in hours. L is length of longest stream, which we can get from catchment area property. A is catchment area, again we can get it. S is average catchment slope, we can get from length elevation profile. So whether it is small catchment area or medium sized catchment area, catchment properties you have to determine first. There is no doing away with this step, and then you use the suitable methodology. So now using Bhatnagar or Brensby-Williams formula, हमने TC निकाल लिया. So now left our task is R50 TC. वो कैसे निकालते हैं? For that, the whole of the country has been divided into 7 zones, 1, 2, 3, 4, 5, 6, 7, and 26 subzones. Like one is 1A, 1B, 1C, 1D, 1F up to G. 2 is 2A, 2B, 2C. 3 is 3A to 3I. 4 is 4A, 4B, 4C. 5 is 5A, 5B, and 6 and 7 only 1. So total 7 zones and 26 hydrometeorological subzones. This India has been divided by CWC, and this is the map. This is given as figure 2 in RBF 16. Here you can see this is 1A, this is 1B, this is 1C, which we have calculated the Betwa zone like that. So 1A Luni, 1B Chambal, Betwa, D is Son, E is upper Indo-Ganges plain, 1F is middle Ganges plain, 1G is lower Ganges plain, then 2A, 2B North Brahmaputra, South Brahmaputra, 2C Barak, 3A Mahi and Sabarmati, 3B lower Narmada and Tapi, 3C upper Nadi, they are basically river basins. 3D Mahanadi, 3E upper Godavari, 3F lower Godavari, 3G Indravati, 3H Krishna, 3I Kaveri. This is actually Krishna and Pennar now, 3H. 4A is upper eastern coast, 4B is lower eastern coast, 4C southeastern coast, 5A Konkan, 5B Malabar, 6 is Andaman Nicobar, for which report is yet to be published. For this there is no report, and 7 is Western Himalayas. So except 6, for all other zones there are joint CWC flood estimation reports, and they keep on revising once in 20 years or so. And which zone is there? Again, based on latitude, longitude of my bridge, I will find out in which subzone my bridge is located. Now, what will happen based on this? As I told you, some of these gauging and data is available for very long. They are older instrumented zones. So, these 7 zones, 1G, 2B, 3B, 3C, 3D, 3F, 3H, their data is available. 50 years, 1 hour rainfall values are available. That is the most accurate. So for these 7 zones, if you are falling in these 7 zones, then you get 50 years, 1 hour rainfall value. And how will get? For this first zone, figure 3.2, second zone 3.1, second 3.2, like that. There are figure 3.12, 3.7 in again RBF 16 report. They look like this here. Again, longitude and latitude. This is let us say for zone 3B, it is written lower Narmada and Tapi, 3B, 50 years, 1 hour rainfall. So contours are there, like this is for 70, this is for 80. So wherever your bridge is there, accordingly, nearest to contour you take and do linear interpolation and find out R51 directly. But be careful, many of these maps there is a remarks here, like in this it is there. Values read from this map are to be multiplied by 1.15 to obtain 60 minutes values. So there you may have to multiply this value, whatever value you are getting. So for that value from this graph multiplied by 1.15. So you will get R51 straight away because this is most accurate. So wherever accurate data is available, we will use that. But for every zone, this data is not available. So next, 9 zones, sub-zones rather, 1B, 1D, 1E, 1F, 3A, 3E, 3I, 4A, 4B, 4C, 5A, 5B. There, what is available is 50 years, 24 hours rainfall values are available. 1 hour data is not available. And these are available in this figures 3.8 to 3.16. So from this, you obtain 50 years, 24 hour value, and a ratio is given in the same maps to convert them into 50 years, 1 hour rainfall value also. We'll see. And then you convert to 1 hour. Like let us say this is for zone 1D, 50 years, 24 hour rainfall value. So this is map. Here you see wherever your bridge is there, nearby contour you take, convert, and here ratio is given 0.37. So this multiplied by this ratio, you will get 50 years, 1 hour value. Now somebody asked me this question sometime back, कि साहब 50 years 24 hour rainfall value तो आपने figure 1 में भी बताया था, जहां हमने R निकाला था, यहाँ भी 50 years 24 hours rainfall value है, फिर difference क्या है? Did you get this question? In figure 1 also you are getting 50 hours 24 hour rainfall value, isn't it? And here also you are getting 50 hours 20. So what is the difference? Did you get? Is it a legitimate question?
Yes, sir.
Now difference is वो मैप पूरे इंडिया का है, उसका स्केल बड़ा है, उसमें एरर ज्यादा, whereas on the same A4 or whatever A3 size, this map is only for this subzone. Otherwise values are same. ये उसी का blown up एक छोटे स्केल पे उसी का वर्सन है. Values will not come different. But वहाँ पढ़ने में आपको दिक्कत होगी. वो मैप पूरे इंडिया का, this is for particular zone. So therefore use this maps as against that. Otherwise there is no difference. Okay, right. So अब मान लीजिए आपके पास आप इस जोन में हैं या इन जोन में हैं, 7 तो यहाँ कवर हो गए, 9 यहाँ हो गए, तो यहाँ आप डायरेक्टली 50 years 1 hour value पढ़ लेंगे. Here you will get 50 years 24 value multiple. But there are some zone for them even these values are not available. We have only covered 16, whereas there are 26 report. So for those zones, those are the zones 1A, 1B, 2A, 2C, 3G, 7, etc. There again you have to go to same figure 1 जो मैं बता रहा था, जो इंडिया का मैप है, this map, same first वाला, उसमें पढ़ना थोड़ा मुश्किल है, scale is bit bigger, so आप इसमें जाके यहाँ से value ले लें and then multiply that value to 0.37 to get 50 years 1 hour rainfall. So by either of this method, now what you have got is R51, and what we are interested is R50 TC, right?
Yes, sir.
Yes, sir. Right. So R51 को अब R50 TC में हमें convert करना है. So for that there is a figure 4 in this report. This is figure 4. This side is TC. This side there is a ratio, and for zone 1, 2, 3, 4 graphs are given. If your zone happen to be 5, 6 or 7, you use graph for zone 4, क्योंकि 6 का तो डेटा ही नहीं है, 5 और 7 का भी डेटा बहुत कम है, so ये ग्राफ नहीं डेवलप हुआ. Now first what you do is this ratio you have to read for TC hours. Let us say your TC is 1.5 hours. So for 1.5 hours you go like this, and let us say your zone is 3. So this is my zone 3, and you read this value. What you read this value? 0.45 something, 0.46. Then for 1 hour time, same chart, you read this value. This will be 0.375 or whatever. So this ratio you will read for TC hours and you will read for 1 hour. So 2 values of these ratio you will read from figure 4. And then a coefficient K will be TC hour ratio oblique 1 hour ratio. 2 values we have read from point 4. And now R50 TC will be K times R51. R51 हमने पिछली स्लाइड में निकाल लिया था, multiplied by K, that will be R50 TC. And what we are interested is in I50 TC or I50, it will be R50 TC divided by TC. So now you have got all the coefficients, put them in this equation, 0.278 C I50A, all the values you have got, and you will get the Q50 value, a minor size catchment or small size catchment area. Clear हो गया?
Yes, sir.
Yes, sir.
Now let us solve an example quickly of calculation of Q50 for a small size catchment area. Then we will see briefly 2-3 slides about hydrograph, and we will see कि medium size catchment area के लिए ये कैसे solve करते हैं. That will complete our design discharge calculations. Then we will go to bridge planning. Right. So this is an example for a small catchment area. This is an actual railway bridge. Bridge number is 185. This is located in Igatpuri Bhusawal section of Central Railway. Its latitude is 20 degree 15 minutes, and this is how you get normally degree minutes, seconds में नहीं मिलती है location. So this is latitude, longitude. Catchment area of this bridge has been found to be 12.43. With this you can calculate also, in fact, using the same GIS method. And length of longest stream is found to be 7.42 kilometers. And height of farthest point above point of interest along the riverbed is found to be 200 H. And the catchment is described as mostly cultivated and slightly barren. Subzone it falls into 3B, and we have been asked to calculate Q50. Now area is 12.43 square kilometer. So this is a small size catchment area, 0 to 25 or less than 25. So we will start calculating. Very simple. Step 1, A equal to 12.43. We know. First is calculation of C. Now if you see the table and try to find out most nearest entry for mostly cultivated slightly barren catchment, this formula, this is para, and that report we have seen, this will be the formula. C equal to 0.415 R into the F to the power 0.2. So now come to R and F. R is 50 years 24-hour rainfall from figure 1 of RBF 16 for the given bridge location. It will come out to be 19.5 centimeter. You have to read from this figure 1. This is how this value will come out. It is between 19 and 20 contour. Then TC, time of concentration. This is not in West Coast, not very small length. So we will use Bhatnagar formula, L cube by H to the power 0.345. This is L, this is H, this power 1.28 hours. So time of concentration for this is 1.28 hours. Come to aerial reduction factor for given value of A and C. Now this is between the last column, it will come between 13 and 25, and TC is 1.28 hours. So 60 to 100 minutes in that. So last column, last row from that table, this aerial reduction factor is 0.86. Okay. So you calculated C, 0.415, R, which is 19.5, F is 0.86, and your value of C will come out to be 0.73. Calculation of I50 from that figure 4 for zone 3, TC hours ratio 0.425, 1 hour ratio 0.38, K will be TC hour ratio divided by 1 hour ratio, so 1.118, and R51 will be 1.15 into 65, so 74.75. This is your R51. R50 TC, K times R51. So R51 is 74 point this, K is 1.118, so 83.57 millimeter. And I50 will be R50 TC divided by TC, so 65.29 I50. Now you got everything. 0.278, C was 0.73, I50 this 65.29, and A was 12.43. So your Q50 for this comes out to be 164.7 cumex or meter cube per second. Very simple. ठीक है?
Yes, sir.
Try to solve one example if you get time. Take some other bridge, or when you go in field training, you will go in open line, you must have gone in construction project. I have seen some report also in East Coast Railway. Some of you have said they have done design discharge calculation. Take the same data and see, in that some data is there, use that data, and RBF 16 I have copied in your course content folder, and it is available on RDSO website. It is, you can get it freely from the net, and just calculate for one, you will get an idea. There was a group which has gone to East Coast Railway, I think, isn't it? And I remember having seen a report, I think, which group it was, Ashwini Moria? Ashwini. And who else were with him? There must be 3-4 people. नहीं है. Hello. Hello.
Yes, sir.
You are able to hear me? Okay.
Yes, sir.
Yes, sir.
कहाँ है? Where is Ashwini? Anjani, sorry. Anjani Moria. Yeah, I got Ashwini wrong. Ashwini is railway minister incidentally. Anjani Moria. Anjani, आप गए थे ना ईस्ट कोस्ट?
गुड मॉर्निंग सर.
गुड मॉर्निंग. आप ईस्ट कोस्ट कंस्ट्रक्शन में गए थे ना शायद ट्रेनिंग में?
यस सर. सर महेश इज स्पीकिंग सर.
हाँ महेश, आप भी उनके साथ थे?
यस सर.
उसमें वहाँ आपकी रिपोर्ट में मैंने one of the reports I remember before we started online classes, there was a report about design discharge calculation for a bridge in East Coast Railway.
यस सर.
तो उसी एग्जांपल को आप अपने इससे, या वो जिस कैचमेंट एरिया में आता है, मीडियम या स्मॉल, टेक सेम एग्जांपल एंड जस्ट ट्राई टू सॉल्व इट. एटलीस्ट 4 of you will get an idea how things are actually done. It will take very less time.
ओके सर.
अंजनी को क्या हुआ? वेयर इज अंजनी? नहीं है. अभिषेक?
सर चैट में मैसेज आया है.
अच्छा,
ऑडिबल का.
ऑडिबल. अच्छा, वो काम नहीं कर रहा है वॉइस. ओके. I think he was also part of that group. I was using his name wrongly as Ashwini. Ashwini is our new rail. Incidentally, he was one batch junior to me in my college during our B. Then he went to IIT Kanpur and did his MTech from there. Okay, so and others also, take some example. Whenever you go to some field location, nowadays by your mobile itself you can take latitude, longitude. So whenever you are standing on a major bridge, just switch on your compass, or you can put a compass app in your mobile and you can note down latitude, longitude. And as you have seen in this example, that once you know the latitude, longitude, everything you can calculate. So just use RBF 16 and consent CWC flood estimation report, whichever is applicable, and do it once, everybody, all of you, you will get a good idea about how actually it fans out. ठीक है?
Yes, sir.
Okay.
Yes, sir.
Now let us move to
Yes.
second part, medium size catchment area. So for medium size catchment area, as I told you, we develop synthetic unit hydrograph. So just few basics of hydrograph. You are all aware what is hydrograph, but some terminology, let me just revise it for you. What are the hydrographs or flood hydrographs? Actually, your flood hydrograph consists of two components. First component is a plot between time on x-axis. Now time can be starting from 0, 1, 2, 3, 4 hours, or it can be actual time, 12 hours, 13 hours, 14 hours, 0 hours, again like that. So this side is time, and we are talking about what we call as DRH, direct runoff hydrographs. Okay, so initially it is total flow, runoff or discharge. A plot between time and runoff is hydrograph. This is one component, but any hydrograph is not complete without second component. That component is precipitation or rainfall versus time, which is in the form of bar chart. Let us say in this 1 hour you had this much of rainfall, then this 1 hour this much of rainfall, this 1 hour this much of rainfall. So for this storm, this was the response. So this combined your storm and direct runoff discharge, these two are put on your flood hydrograph, especially your direct runoff hydrograph. Am I right? यही है ना hydrograph? ठीक है या नहीं है?
Yes, sir.
Yes.
Okay, sir.
Yes, sir.
Yes, sir.
I have studied hydrograph more than 30 years back, so I might have forgotten, but you are all fresh from colleges, so you must be knowing better than me. So hydrograph is a graph showing rate of flow discharge versus time at a specified point in a river. Of course, the point where we are doing gauging or where we are doing the measurement, it actually shows two graphs, one showing your precipitation and other showing the discharge, as we have seen. And of course, this is not useful, but why do we construct hydrograph? First, to find out the discharge pattern of a particular drainage basin. You are trying to establish a relationship between rainfall and your discharge. That is one purpose. And in fact, they are also used for predicting flood events. Let us say this is my hydrograph. Then I know what is known as basin leg from here to here. That if rainfall occurs in basin leg, the time by which my maximum flow will build up at my point is this. So this is the lag. This is the time available with you for forewarning the people. So the moment in your basin or in your watershed or in your catchment there is a rain more than your whatever values you have decided, you will get a forewarning that basin lag time 6 hours, 8 hours, 10 hours, and you can use that time for evacuating the people. So this is another purpose. Now this is how we said this is time, this side is discharge, and then another is time precipitation like this. This is how your hydrograph looks like. Now discharge, sometimes we use term Q, its unit can be Q max. Sometimes we also use term discharge intensity. It is Q by A. Then you use, then its unit will become meter cube per second per square meter or per square kilometer, whatever. So it can be discharge as well as discharge intensity, both. Then it is useful for us. It has got this limb which is known as rising limb R. We use word R. Then this is the peak point. This is peak flow, which gives you maximum discharge or discharge intensity. And then you have another term which is known as recession limb or falling limb, F. R limb and F limb. That is what we call them, rising limb and falling limb of your hydrograph. And this from center of your precipitation diagram to here, this is your basin lag time, PP. So from the center of rainfall diagram means when your rainfall to maximum build up point. This also indirectly is your TC, basin lag time. Then see something goes in infiltration, whatever rain is there, and that ultimately shows as base flow in total discharge. So this is base flow line. Now there are various techniques of earmarking the base flow. We will not go into those details. We'll just use a straight line method, and we will use only this part of hydrograph. And since we have deleted base flow mid, what we are talking is only direct runoff hydrograph. DRH. We will be using DRH for our purpose. So this is how a flood hydrograph looks like, and these are its components. Now what is unit hydrograph? Yes, anybody? You are all good. What is unit hydrograph?
It is the plot of discharge against the time for a rainfall having unit intensity.
Unit intensity, good. It is a response of, or it is a hydrograph for unit intensity lasting for a given duration. So unit hydrograph also is for a duration. Unit hydrograph for 6 hours, unit hydrograph for 12 hours, unit hydrograph for 3 hours. So lasting for that duration, a unit rainfall. So unit hydrograph is a DRH, direct runoff hydrograph, resulting from 1 unit depth, we take 1 centimeter in our case, of rainfall excess, means runoff, occurring uniformly over the basin. Assumption is it never occurs, it occurs at some point, but we assume that it is occurring uniformly over the basin. That's why there is an areal reduction factor and conversion factor, and at a uniform rate for a specified duration. So it is 1 centimeter d hours rainfall. For that, whatever is my hydrograph, so let us say this 1 centimeter rain which lasted for 6 hours, 0 to 6 hours, and if this is my DRH for this, this will be called 6 hours unit hydrograph. Simple. Now there are 2 principles or 2 assumptions in unit hydrograph which are not very off the mark also. They are very useful, and they are very useful for us, for our purpose, at least when we want to do design discharge calculations. What are those assumptions? First is known as time invariance. Time invariance means, let us say this is my hydrograph and 6 hours unit hydrograph, let us say I am plotting. So this is 0 hours, this is 6 hours, and this is unit rain, and this is my unit hydrograph. Okay. Now it says this shape will remain same irrespective of at what time my rain has occurred. Now let us say rather than happening here, my rainfall has occurred between 6 to 12 hours. Then it says this graph will only shift by 6 hours, but otherwise it will remain same. This will only shift here. This is known as time invariance. It does not vary with time. Only thing, it will get shifted with time. So that is principle of time invariance, and it says this means that a direct runoff hydrograph DRH for a given rainfall in a catchment is always the same irrespective of when it occurs, right? And second is linear response. What is linear response? Linear response means, let us say again we take an example, 3 hours or 6 hours, whatever, there was unit rainfall and this was my hydrograph. Then it says if rainfall was n centimeter rather than 1, it is n centimeter. It says its shape, its extent, everything will remain same. Only thing is every ordinate of this will be multiplied by n, and this will be my hydrograph. Linear, the response is linear. So if rainfall is more, this will get multiplied by n, everything, and this will be my hydrograph for n centimeter of storm. Direct rainfall response to the rainfall excess is assumed to be linear, like this. This was unit hydrograph for 1 inch, then for 2.4 inch you multiply by 2.5. This will become my hydrograph. Clear? I hope up to here ठीक है, यहाँ तक सब समझ में आ रहा है?
Yes, sir.
Yes, sir.
Now, how it is used for our purpose, that is important, and it is very, very useful. Now, let us say this shape 1, this green color, is my unit hydrograph for unit duration of the rain, maybe 1 hour. Now I have got 3 rainfall spell. First of 1 hour duration of 1.5 centimeter. Second, after 1 hour, 2 centimeter duration, and after 1 hour, 1.25 centimeter duration. And I am interested in finding out the combined response. So first I will plot this one. Then for first rainfall, which is 1.5, using the principle of linearity, I will multiply it by 1.5 and we will plot this 4. This 4 is the response for this. Okay. Now, next time, for next 1 hour, the same one I will shift by 1 hour, starting from here, which is 2 now. This one, 2. And then it is 2 units. So I will multiply all these ordinates by 2. What you are seeing as 5 here, this 5. So this will be my response of my catchment for this 2 hours rainfall. Similarly, in third hour, it is 1.25. So first I will shift this 2 hours, what you are seeing as 3, and multiply by 1.25. That will become 6. So now my response is 4, 5, and 6. And then at every hour, I will add the ordinate of 4, 5, and 6. And this will be my combined response of my catchment to this rainfall. So by using this principle of time invariance and linear response, any type of design storm, I break them into 1 hour storms of whatever duration, apply